Now here, you can use asymmetric cryptography to guarantee authentication, but you will inverse the use of the keys. Okay? So instead here, you have a message M, and this is Alice. Alice wants to send something to Bob, but with authentication. Yani the communication should have the authentication properties. What you do, you sign your algorithm. How this is done? Basically, you encrypt the message with the sender's private key. The sender's private key. So you have a public and private key. You encrypt it with your own private key. So basically, who can decrypt that message?
Anyone with your public key.
Anyone, because it's public, so anybody can decrypt your message. But only you can send that message. Only you can sign with your signature, of course. Okay. So here you encrypt the message with your own private key, and then you send both the message and the signature. And here, basically, if you encrypt all the data, do you need here to send M?
No, you send the hash.
Yeah. Here, because it says signing algorithm. So you encrypt here all the message. If you encrypt all the message, all there. So it's all in there. So basically, the signature is the data at the same time. Okay. So additional signature needs a public key system. The signer signs with the private key. The verifier verifies with the, of course, at the verification side, the bot will use its public key to check that the signature is valid. Yes.
In this case, what's the difference between encryption and signing?
It's opposite. Basically.
Encryption.
Yeah. Encryption using the public key.
Asymmetric.
It's both are asymmetric.
But what's the difference between signing and
what is the difference? Who can
It's what?
You reverse use of the keys. When you need to just encrypt, you don't encrypt your message with your own private key. You encrypt it with what?
The public key.
With the public key of the recipient. You see, this is the difference in the use of key. Either use the public key of destination or use your own private key. Yeah. Okay.
And this is to make sure that the one who signed the file is the one I want to receive the file.
No, here to make sure that only you can send that message.
Yes.
Only you can send that message. You can sign that message. No, send. Okay. So here, put yourself in the position of the recipient, the destination. Here, if he receives something, and when he applies the public key of that user from which he received the message, he can decrypt the data and you obtain meaningful data. Okay. And if he does that, basically he is sure that only else would have sent that. Could have sent that, okay? Because only else had the private key, which is mapped to the public key, okay? Is it clear here?
Yes, but now the message is the signature in the tail of the message, or embedded inside the message scanner.
Here, just you will send it. You concatenate the data basically. You should have a message, a way to put that into buckets and then send it.
Yeah, but if someone in the middle intercepts the message,
yeah.
in case I can send them another message with his signature.
No. He can send another message, but how? Okay, it will appear as coming from somebody else. It is impossible that that user, that attacker, can send another message and claim to be coming from else, because
He doesn't have the private key.
he doesn't have the private key of else. And to sign, you need the private key of else.
But since you said you concatenate them,
Yes.
you just have to take it out.
Take it out.
Concatenate
Yes.
something else. Another message.
But the signature is related to the data. Here we took M, and from M we generated the signature. The signature is not a generic piece of data that you can merge or add to any. It is related to your data you want to send. Okay? Here we are signing by encrypting all the message. Okay.
Why don't we just?
I'll come to that. I'll come to that. So crypto system here meaning using asymmetric cryptography for encryption to get confidentiality. Okay. A crypto system uses the private key and public key for the receiver. Okay. A digital signature. Now, if you need to use asymmetric cryptography for digital signature, it uses the private and public keys of the sender. And both here, because if you need to encrypt, you need to use the public and private key of the destination. If you need to sign, all the scenario uses the public key and private key of the sender. Okay. Is it clear here? Now, I'll come to your point. So basically, doing this, basically signing all the message or getting the signature out of all the data. Is it practical? Is it efficient?
Takes long.
And we saw that one of the disadvantages of asymmetric cryptography is the efficiency. It's not efficient. Okay, it's slow. Okay, compared to symmetric cryptography. So here, instead of signing all the message, okay, all the data, if you want to send, I don't know, 10 megabytes, you need to sign all those 10 megabytes, which takes time. So basically what you're going to do, you will get the digest, a hash of that data, and then sign only that hash. Okay? So basically it is better to sign only a digest of the message. So basically what you do, this is your message, you compute the hash, you obtain some hash value out of that data, then you encrypt it, so you sign it basically. You sign just the hash. You take that digest and you encrypt it with the private key, and then you send both the message and the signature. And here you need to send both message and the signature. Okay? So you send both the message and the signature. At the destination, you will decrypt the signature. Yeah. Okay. Then you apply basically, yeah, you start from the message. You apply. You repeat the same process. You compute the hash, and you encrypt the.
Decrypt the signature.
Verify that they're.
Yeah. So basically, here you're gonna have a hash. Now you take that signature and you decrypt it with the public key of sender, and then you compare. Okay. Yes, we compare.
So this is good.
Yeah, and basically this is how to get authentication. This is the typical way to guarantee authentication. So basically, you compute a hash, you sign it, and then you send that signature along with your data. Okay. So here this guarantees authentication. Does it guarantee confidentiality? Doesn't. Does it guarantee integrity?
No. Man in the middle attack.
Yes.
Yes. Integrity, it is guaranteed. It is guaranteed.
You can't change the message. If you change it, the other person will know that it has been changed.
Yes. So integrity is here. Integrity with authentication, you are fine. You are even safe from man in the middle. Yes. Okay. Because man in the middle, as we discussed last time, you can take the message, compute another hash, and you start from another message, modified message, compute this hash, and send both. But here you can't. You can't because you need to sign that hash, which you couldn't, because you need the private key of the sender. Yes, somebody.
But then you can have your own private key, the attacker.
Yeah, of course, but here it will appear that you, as an attacker, sent the message.
Still, you can act as the server, spoof being wrong.
No. Here see, when you say, okay, Alice has a private key and public key, we have, if you use it in practice, you have a certificate for every pair of keys you have. Okay, so basically, the owner of a public and private key is guaranteed by some trusted authority. Okay.
It's the same method used in SSL.
Yeah, SSL uses this, of course. It uses, but of course, an improved version of this, okay, with more details. Okay, but in the heart of it, it uses this. Okay. Now, digital signature can directly provide authentication, integrity, we discussed about it, and non-repudiation. Now, we didn't talk about non-repudiation. Everybody understand what's non-repudiation? So basically, you cannot deny having done something. Okay. Now, we saw how we understand how to guarantee these, but how to guarantee non-repudiation? Okay.
You check with some person says that he didn't send that message. You do the decryption with his public key and see if it decrypts, then he sends.
Okay, so basically if A sends something to B, okay. Now, A, after let's say a month, it says no, I didn't send that. I didn't send it, okay. Now, B, what it can do here? What it can do?
Decrypt with the public.
So basically, it keeps a log. Okay, these are the messages I received, etc. And basically, I received this. Let's say this message at date X, and it is digitally. Basically, if you use a digital signature, so that the message will be signed with the private key of A, and only A had that. But still, here A can claim that it is not my key, or basically if it is expired or whatever. Now, always to guarantee non-repudiation, you need a third entity. You need someone here, we call it the trusted center, okay? Trusted center, where if A wants to guarantee non-repudiation, basically if needs to send, let's say, a warning or something to B, and to get that non-repudiation property, you need to send it first to the trust center, and then the trust center will forward it to me. Okay. So this is how it is done. So basically, Alice will have a message, will sign it with its private key, and it will send it to the trust center. The trust center will check the identity of Alice, okay, and then it will get the message and encrypt it with the private key of the trust center. So it will not just forward it, okay? It will encrypt it with its own private key, and it will send it to the destination. Okay. So here, if Bob, if everybody trusts the center, Bob cannot deny. Okay, Bob cannot deny having received that message. Okay, and here, Alice cannot deny that it has sent a certain message. Okay, because we have a trusted center that will keep a log of everything that happened. Okay, now non-repudiation is provided by having a third trusted party. Okay.
Yes. Non-repudiation is like both ways.
Yeah. Yes.
Because Bob can't deny. I didn't receive anything.
The message is lost in the network.
Yes. It can deny. It haven't said. I don't know. There should be some acknowledgement mechanism when you acknowledge. Okay. And this is the network. Okay. If this is related to TCP, TCP has this feature. You need, for every message, if you don't receive an acknowledgement, you need to keep sending it again. Okay. So it's not network layer. This is the issue.
Doctor.
Yes.
The trusted center, what is it in real world?
I don't know. If you need to guarantee non-repudiation in some network, it might be I don't know the gateway or an administration host in the network. Okay. In a more general, larger environment or context, it would be some server, some website. Okay. So, for example, if you use TeamViewer, all the communication go through one server. Right? You don't communicate directly with the destination. Okay? All the communication go through so it might be a server that will play the role of proxy somehow. Okay.
And this is what happens in real life. There's no direct communication between Alice and Bob.
Of course, there is no. But you will go through a set of hosts, okay, or hops. There is no. The only direct communication is between a machine and the next hop, which might be a switch, it might be a router, or any network device. Okay.
Sir,
Yes.
why don't we to send the message back to Bob and the signature goes to the trusted server. Wouldn't that be faster?
So basically, what you do, if you have a message and a signature, you will send the message to Bob and
Yeah.
then the signature.
The signature goes to the trusted. Same paradigm as the previous.
Only the signature goes.
But here the point is we need to
the trust itself.
send the same message encrypted with the signature of
Yeah,
the
but
trusted
we
sender.
send the hash with the signature,
Then.
and the message goes alone. I mean, we only care about the signature to be trusted.
But non-repudiation is that.
What if the trusted source wants to check if the whole thing works?
If the message itself is.
So the message is really, but this can be checked at Bob. Yeah, here, Bob can claim that the message is not really the one corresponding to that signature.
Yeah, because they don't keep lock.
Because the trusted sender has no way to check that message.
Also, the message can be attacked from the trusted center to the Bob. It doesn't have signature. We need to fight at Bob.
Yeah.
No, Bob should have the public key of Alice and should have the public key of everyone that sends.
It has that.
But here it has only the trusted center's keys. Public.
Yes. So here basically it doesn't need to have all public. Just there is one trusted center. Everybody has the public key of this trusted center, and that's it.
That's it.
Yeah. Simpler. But here it has some. At least this scenario is better. Okay. Maybe it's more efficient. Like what you're talking about. This scenario. But if we need to dig more, you will find holes in the scenario. Yes.
Very interesting. The private key for Alice, how secure is it? Couldn't someone, like, for example, find out it's the.
It's the same thing. It's computationally invisible.
But it's maybe because there are so many operating systems and so many versions of Windows, maybe they use the same mechanism of
Generating.
Yeah.
No, this is generation of the key is assumed to be secure. The algorithm, RSA, for example, we saw what's the problems. One of the problems is the implementation of the algorithm. How it is you can have flaws. It can reveal some information that allows to guess what is the key. But here, whenever we whenever we use this algorithm, we assume that the keys are difficult to guess. Difficult, maybe computational invisible. Okay, to guess that. Okay, we assume that. If you don't assume that, we have a lot of problems. Okay.
Are they changed over time or?
Yeah, we discussed this time. Basically, the private and public keys, how much duration it will stay.
Years. 5 years.
It's what years? It's at least 6 months. Okay. The public and private key, the certificate. Go to your browser and check the certificate, and you see the expiry date. You'll see it's like 2019, 2020, stuff like that. But the symmetric key, the symmetric keys, now they last for a short period of time. Symmetric keys at 5 minutes, stuff like that. Okay.
Is it because they are easier to do?
Yes.
Brute force.
Yeah. So basically, because the public and private keys, they are basically used for what? The asymmetric part, asymmetric cryptography part. It's used for
The
Key
key exchange, key agreement, basically. Key agreement. So it's not very much used. It's like 3-4 packets and that's it. But for the symmetric key, all the data, because if someone wants to get enough samples to crack it, okay, it will have a lot of them. But for asymmetric, you just in all the communication, you will have the 3 or 4 first packets, and then that's it. Okay, you don't have enough samples. Okay. Adding confidentiality to a digital signature scheme. Because all the previous scenarios, they don't have confidentiality. Okay, to guarantee confidentiality, basically, you need to here using asymmetric key. Basically, you encrypt the data with your private key. This is to guarantee authentication, and then you take the result and you encrypt it with the destination public key, and this to guarantee any confidentiality. At the other side, you do the reverse. Decrypt with Bob will decrypt with its own private key to decrypt the first layer. So you have 2 layers of encryption. Okay. And then you decrypt with the Alice public key, and you to get the message. Okay. I'll discuss. This is not the best scenario to guarantee authentication and confidentiality. We're gonna discuss it. So yeah, digital signature schemes. You can use RSA. In general, all the other RSA, asymmetric key cryptography techniques can be used for digital signature. So for RSA, you know how it works. So basically, this is the same diagram, but we have more details about how the encryption is done. You remember the encryption, so you compute the modulo with the private key of Alice, and then here you do the decryption with the public key still of Alice, and you check here the message, the signature of the message. Yeah, and this is an example with numbers. Just examples with how the RSA keys are generated. So P and Q, then you get N, then you compute 5N, then you have the public. So public key is 313, and the private key is this number. So you encrypt with modulo, etc. Just an example of numbers. Same thing. So here basically the same scenario, but instead here we're gonna use, we will encrypt we'll sign the hash, the digest of the message. So we use the hash function and take that digest, and then we encrypt that digest, not all the message. Okay. This is the standard scenario. When the solid instead of the message served, the stability of the distancing scheme depends on the strength of the hash. Yeah, you need the hash algorithm to be strong enough. Yeah, that's it. So okay. Before we cover something else, I want to show you something. So there is, if you need to, you can start now playing with the cryptographic algorithm. We're gonna have assignment 2. About this. Homework 2 will be about writing code in either Java or any language you are comfortable with to encrypt data before sending it. Okay, so it's very secure communication between 2 parties. So there are tools where you have all these algorithms implemented. If you use Java or C or Python or whatever, you have libraries to use all those algorithms. But there is a small tool here, it's called the crypt tool, where you can get any message and crypt tool. So and then you encrypt it. So this is the interface. You can download it. It's written in Java. Then this is the message. This is the data, and you need to encrypt it using some algorithm. So you go to the menu here, encrypt, decrypt, and you pick symmetric, classic. These are the old, kind of ciphers, very quite simple ones. Okay, Caesar, Visionaire, Hale, etc. XORing, but the cryptographic one are these. So symmetric. So you have RC2, RC4, DES, triple DES, and then AES. Okay. Now here you can. So let's say DES, this one, the first one. Okay. So this you pick the key, and then you click encrypt, and this is your encrypted data. Just very simple. Okay. Now. There is one detail we didn't cover, which is this one, symmetric, and then if you see DES here, you see ECB and CBC. What is this?
This is padding.
Huh?
This is electronic code book, and the one for the padding, when you have a big data and you want to, for example, if I want to attack the system, and I know that this block might contain, for example, the salary, and I have, for example, a block that.
See, this is it. But as simple as this, if you remember DES and also AES, okay, DES and also AES, and also hashing. No, hashing is a bit different. But you have big data, right? Okay. So what you do to encrypt it, you split it into blocks, right? You split it into blocks, and then as we discussed, you have in mind now, you take the first block, then you encrypt it, okay, E, and you get some data. Okay. Then for the next block, you will do the same thing, okay, encrypt it, and you get the another block, and then at the end you will repeat the same thing and merge or add all those blocks together and send. Okay, this is the simplest mode. Here we are talking about a block cipher. How can we deal with this? Is it just independent? Because it's independent is less secure one. Okay. Now block ciphers you have several. So what is it? So I'm going to just Wikipedia. So this is called block cipher mode, the mode of operation. How you do that? So the simplest one is this one. Okay, so basically
Electronic code.
Yeah. So here electronic code book. So basically every block is encrypted independently from the other blocks. Okay, and the decryption the same thing. Okay. Now this is ECB. Then the next there are several. So for example, cipher block chaining. Block chaining, it's chaining. So basically, you encrypt the first data, but once you have the encrypted data, you will have the ciphertext, but you will use that ciphertext to XOR it with the next plain text data. Okay, so that you have some kind of dependence between all the blocks. Okay, so you take that previous block and you XOR it with this, and then you encrypt it. And the same thing here. So you are chaining. You are chaining the blocks. Okay. So you have several. This is one mode. This is the decryption. Then if you go down, you have this is what? This is propagating cipher block chaining. Here you do something quite different. So here you merge at the starting and then at the plain text and the ciphertext. Okay. You XOR. Anyway, so different mode. It's about just how to combine the ciphers of every block. Okay. Okay. So once we did this, now we will do something very interesting. We will summarize all what we did so far. Okay. So the encryption mode is ciphers, etc. Now we use cryptography to guarantee some security properties. Okay. So the security properties are basically here what we saw. We saw confidentiality, we saw integrity, we saw authentication, we saw today, and non-repudiation also today. Okay. Availability, with cryptography, it's not really any use. We have other techniques to guarantee availability. Now, if I tell you, you have a message M, okay? You have a message M, and you need to guarantee, for example, just confidentiality. Okay, confidentiality. Okay, confidentiality. Okay, so how are you gonna do with that? How are you gonna send M? Encrypted with what?
With the receivers,
Asymmetric.
So basically, we can do it several ways. Basically, in two ways. Okay. Symmetric and asymmetric. So basically, you can encrypt it with the. When I say EK here, it means the secret key, symmetric. Okay. EK of M, and then you send that, and then you send it. This is to guarantee a confidentiality. Now you can do it another way. You encrypt it with what? Here to guarantee confidentiality, you need to encrypt it with the
receiver.
The receiver's public key. So basically here encrypt with, let's call it PBK, which is the public key of receiver. So okay. So basically here you can do it with symmetric cryptography asymmetric. This is to guarantee confidentiality. Now to guarantee integrity. How are you gonna do? So you need the hash. So basically, you take the message M and you send it along with the
Encrypted cigarette.
with the hash. If you need just integrity, Basically, you send the message, okay, along because you need to send the data. So here, when I say bar, it's just concatenation. Okay. So with H of M. That's it. This will get just integrity. Okay. Now, if you need to guarantee authentication. Okay, authentication. You need to do what?
take the message.
So basically, you can also do it in several ways. The simplest way is to send the message along with
Hash.
the first without hash. Can we do it without hash?
Yes.
We just basically we need a signature of all M. So basically, encrypt with private key, okay, of the sender, okay. So you send both these two. You guarantee authentication, okay. But also the better way would be to send message along with
The hash message.
the
No.
encrypt private key of hash of M, right?
Yeah.
That's it. Okay. So this is to guarantee authentication.
Yeah.
Now,
For this one, sir.
Yes.
that one, we don't need to concatenate, right?
why?
Because.
Basically, we need to send both of them.
Okay.
We need to send both. Now, if you need non-repudiation, just non-repudiation. Non-repudiation. So basically, you need to send M to the trusted sender, right?
Yes.
So you need to send it to the trusted sender. Okay.
Signed.
Yeah, signed. Here, basically, you need in that case, you need to send all this to the trusted sender, right? Now, to guarantee confidentiality and authentication. Confidentiality and authentication. So basically, confidentiality plus authentication. So here, basically, you need to have
Encrypt everything.
all this,
Encrypt.
and you encrypt it with a symmetric key.
The public key.
Or the public key. So here you can do it in both ways. But typically, if you need confidentiality, most of the time you're going to use symmetric key. So here you need to encrypt with the symmetric key all that M, then encrypt private key of H of M. That's it. Okay. Now you can combine, for example, if you need confidentiality and integrity.
You encrypt the message and the hash.
Confidentiality and integrity. Basically, you encrypt the message and its hash. Okay. So confidentiality and integrity. So basically, you'll encrypt, and then the message and the hash of M. Okay. Now, if you need confidentiality, integrity, and authentication. Confidentiality, integrity, and authentication.
You use your key and their key.
Use this, yes.
This one is nice. Here it will guarantee everything. Yeah, not everything, but now this guarantees confidentiality, authentication, and integrity. The three of them. Now, if you need to add non-repudiation, you need to send this to the trusted center.
Teacher, the signing guarantees integrity, right?
Signing, yes. So the signing, signing the hash.
Yes, all the message.
So basically, this one.
Yes.
Does this guarantee integrity?
Yes. Yes, because it's
Authentication is process.
well,
No one can.
Yes, this guarantee also integrity, right? Because nobody can change this
yeah.
without knowing the private key. Okay. So in order to change something that is meaningful, you need to decrypt it and then change it and sign it again, or encrypt again with the private key. Okay. So yeah, this summarizes all this part. Now, still we have the issue of the symmetric key. Because asymmetric key we are done. Basically, we know how it works. No, still, in both symmetric key and asymmetric key, we have the issue of the key distribution. Both. With asymmetric key cryptography, you need to send the public key of your public key to all the users in a secure way. Because if you don't do it, somebody comes in the network or in the system and claim I have the public key of that user. Okay, and if we don't have authentication ways, people will so
what's the issue if somebody claims that he has the public key?
it's a problem because he will impersonate that other user.
He cannot send any messages because he doesn't have the private key. So
no, if for example he claims to have the public key of A and he sends that public key, he has the corresponding private key.
Exactly.
The attacker has the corresponding private key of that.
yeah.
So he'll be using that. Key distribution is even more important in symmetric key cryptography because you need to, both entities, in order to use symmetric key cryptography, they need to agree on the key, on the secret key. And this is also, it requires some particular protocol. Okay. So next time we're gonna see key distribution.